Hello, my name is Cleveland Crossling, and I'm going to be showing you my artificial intelligence project for this semester. Um, so what I did is essentially maze generation with depth first search, um, which is done in two parts. The first part is finding a solution that is greater than a desired depth, and when that depth solution is found within a space, then the empty spaces are filled in with another depth first search recursive algorithm, which essentially fills in the whole maze. So then there's a second agent which solves the maze using Q-learning. It is separate to the original agent, so there's no information except for what the maze looks like, or a graph of the maze. And it creates a Q table, the size of the maze, and trains by going randomly or using the Q value in the table when the epsilon is sufficient. Then it shows the actual path taken after that is completed. So, I'm going to run through my code from the top and just explain everything from the beginning. So first things first, I have to define a graph structure. So what I do is I go ahead and I add my nodes, which are the vertices, and they just contain information about their neighbors and where they are in the actual maze, and then the value that they store. And then going through this, I show this is how I create my graph. It's just simple adding edges, removing just typical graph structure, and a simple way to print it. Um, I have my maze agent. This is essentially how the mazes are created. It creates a graph, um, and then takes in the coordinates of all the values that are created. Um, or rather all the values of all the points on the maze. And yeah, it initializes these all to just be 0. So this is what this function does. It just initializes the entire graph to be of the size defined, the grid size, and then initializes them all to be 0 and for all the nodes to be connected to each other. This is just a print maze function. It just prints the maze according to the coordinates. So we get a block. Over here, this is to actually construct the maze. So essentially what this does is it first creates the main path, the solution path. This is the first agent, the solution path. It creates that using this function at the bottom over here, which is called DFS solution. And it essentially goes through the whole maze and tries to find a path that is of the correct size. Larger than the desired depth of the path. Okay, and then once that's done and it's desirable, you'll see there'll be a bunch of prints to the console. So we'll see it's trying to get attempts, and it'll show us a bunch of failed attempts, and eventually it does get one that is long enough. And isn't looping in on itself. Then what it does is it actually goes and does it again with the next step, which is filling in the maze completely, and it does this using DFS dead ends, this function. And this is another recursive function, and it essentially just tries to find a dead spot or a spot that has a 0 on it inside of the maze, and then fills it with a different number. And what that does is as it's filling in, it tries to find the original path and tries to connect back to the original path. And or it connects back to itself. It depends on what it wants to do, but for the most part, it works fairly well. So the next function is full function. Make sure that once we've run through it a bunch of times, eventually we know when the maze is full, and that's how we know. Okay, here's a maze. This might be, this is good enough, and then it passes it through to so I can work with it, so I can actually display the maze. And yeah, so that's what that does. And this over here is just if I'm not wrong, this is just connecting everything within the path. So first it just gets all those paths, the little ones, the dead ends, the ones that don't go anywhere. And then this over here, this function, what it does is it connects all those paths to the main path or to other paths. And so yeah, that just connects everything up. Make sure that the maze actually is a maze and not just all over the place. So the next thing is, so once I have that, I so I do an implementation, which we'll look at now. But this is the next agent. This is my Q agent. It does Q learning. Essentially, how this works is I just pass through the maze to it and all of the hyperparameters that I want to work with. And so over here, I'm just I'm just creating a Q table that's completely empty. It's full of zeros, and I'm essentially just letting the algorithm go through the entire maze and find paths and just train off of it depending on how many epochs there are, and it goes and tries to find it according to the Q learning algorithm, or yeah, the Q algorithm, which is this line over here. It's just essentially how it learns. And then yeah, the next move is picked, whether or not depending on the epsilon value, it will either pick a value that is within the Q table, or it will pick a completely random value depending on the neighbors. Yeah. And next over here is the get solution. This is essentially just it stepping through the Q table. So if the Q table has been sufficiently trained, then this will work. Otherwise it results in loops, but loops are dealt with. So as you can see over here, it does deal with loops. But yeah, essentially it just it tries to find the best path depending on what values are most desirable to step on, i.e. which values are greater. It should probably note that the rewards are, for every step, it's minus 0.1, and for getting to the end of the maze, it's plus 10. So that's how we ensure that the Q algorithm moves in the right direction. Or the Q table rather moves in the right direction. So then finally we just have this draw maze function. This is now moving into implementation. So I load in the images. I'm using tkinter for my canvas and for my components. And essentially what happens is I load in all the images over here. I have to keep a reference of them so that they can load within functions. But there's all the images that I load in for all the different states that I could have, because obviously this maze does account for loops. It has loops in it. That's why we can't solve it with a generic algorithm. And so yeah, I have to account for a lot more different cases than just a typical maze. Like for example, several four neighbor blocks might be next to each other, and so I have to account for that. And so then what happens is it fills in. This is it filling in all of those onto the canvas, and then gives me the canvas back. So here's it adding them all in. This is just where to put them and or which image to put, and then here's it returning it to me. And then over here, this is now my implementation. So I'm generating the maze and just essentially all it does is it just calls the classes. It constructs the classes, and then I just call the functions to actually construct the maze. It's all built in. I just pass through the depth, which we'll get to now when I show my components, and then yeah, it draws that maze onto the map at whatever cell size I desire. Over here is just implementation of the components. This is fairly straightforward. You'll see all that now. Same thing over here. Over here, we're just calling the function to generate the maze. Over here, this is start training. So this is essentially just training the Q agent, building the Q table. All I do is I just call the function like before, and I basically set the path as a global variable so that I can access it in the next function for where we actually step through the path. And over here, this is the stepping through of the path. This is actually now showing every single step that the algorithm took to get to the end. And now I'm just going to just run through essentially how it works. So this is just all my placement on the panel. But yeah, now I'm just going to run through how the actual system works. So now I'm going to run my project, and there you go. This is the interface of the project. As you can see, this is all the parameters I can enter. So first things first, I'm going to now enter the dimensions. So we'll go 20 by 20, and I'm going to make that a depth of, so this is the minimum complexity of the maze. We're going to make it a depth of 20, and a seed of, this is just a random number, and there, it found a maze. that suited my specifications, and this is the maze that it generated for me. As you can see, there are loops in the maze, but if you follow it, you can probably find your way. It says that the depth of this maze is 114. Okay, so now I want to solve it using Q-learning. So we're just going to enter a discount factor of 0.7, learning rate of 0.4 is fine, we'll do epsilon of 0.1 is fine, and we'll do 100 epochs, and all I do is I click train, and okay, so the hyperparameters were not good enough, so it says that it looped at this, so what we can do is let's increase the discount factor, and increase the learning rate, and try this again. And there we go, it found a solution for me. And now all I'm going to do is I'm just going to step through, and it's going to show me the path. There is the path that the algorithm took to get to the end. So for my percepts, what I do is I essentially, each agent has its own percepts and actuators. So the agent of both agents do not know the size of the environment that they're working with. At least while they're busy trying to traverse it, they don't know the size of the environment they're working with. They just get given a graph, and so then they move through that graph, and they try and create something from it. So for this algorithm, for the maze generation algorithm, it uses depth first search to do that, to essentially travel through the maze and generate the maze, and that is done with essentially looking at its neighbors around it and making random decisions of where to go. And it's the same thing for generating the random paths, like the dead-end paths. But the Q-learning does the same thing. All it's done is given a graph and a starting position, and it uses its own, it just goes in its own direction, chooses random directions, or uses epsilon to go in random directions, and eventually it finds a path to the end, and it does it over and over and over for many epochs, and eventually we get a Q-table with the solution. And then the Q-table is now defined space, and we can just follow the largest the largest value in that is the largest value of the next neighbor, and then we just step through over and over and over until we get to the best path or to the solution, and that's essentially what this system does. And so a real-world application of this project is typical applications with Q-learning, which could be, it could be used for pathfinding in an unknown or changing environment, which is nice. It maps the usefulness of squares. So for example, this square up here is not as useful as this square over here, because obviously this square I have to traverse through to get to the end. So that might come in handy for, holding onto that information. For example, looking at people moving through a space. You might not want them to go certain places because they're not as efficient, so this might be a good application of that. And so it could also be gauged, and this is a little bit more literal in what I've done, to gauge the complexity of mazes. We can look at depth, and the longer it takes to train, maybe the maze is too complicated, so we can look at it from that direction as well. Obviously this is a loop maze, it's a little bit easier, but it's still you can gauge it like this. It would work on a standard maze as well, but then it's obviously better algorithms like A-star would beat this algorithm. And that's the thing, is this algorithm can handle loops. So yeah, that's also why I went with Q-learning with this. Yeah, thank you very much for listening to my presentation, and I hope that you enjoyed my project. Thank you.